Hi, welcome to Fluid Mechanic. Today we're gonna solve one question, which is the pump of figure there is to increase the pressure from 0.2 meter cubic per second of water from 200 kilopascal to 600 kilopascal. If a pump is 85% efficiency, how much electrical power will the pump require? The exit area here is 20 centimeter above the inlet area. Assume inlet and exit area are equal. Alright, the first step, what we're gonna do is understand the question. How much the electrical power required? So this is the question. Thus, we need to find the pump power. Alright. So the assumption here, step number 1, assumption, we need to list out all the assumption. Assumption here is the density of the water or the density of the fluid here is water, thus it is constant. And assumption number 2 is, alright, the flow here, the velocity profile is uniform. Thus, we can use the average velocity at 1 and 2. And here, as well, there is no turbine. This is only focusing the pump only. So, applying, so there is no, alright, here there is no turbine. No turbine. And we assume that there is no friction loss. There is no loss, alright, due to the flow. No loss. Alright, so H of L equal to 0 and head of turbine equal to 0. So from here, step number 2, we need to apply energy equation. Okay, we need to apply energy equation. Since this involves of the flow and the pump, it requires the energy. Thus, the energy equation is required. So, energy equation, given that the full, we need to write the full energy equation, which is H of a pump, which is input, plus velocity 1 inlet squared over 2g, plus this is head of pressure P1 over gamma, plus the head due to elevation equal to head of turbine plus V2 squared over 2g plus, and then plus pressure head P2 over gamma plus Z2 plus head loss HL. Since the head loss is 0, assume there is no loss because this is only the small section of the pipe. There is no long pipe. So we assume the head loss is equal to 0. And then there is no turbine, HT equal to 0. Right? From here, and then, okay, and then the velocity here. The velocity, you can see that we can simplify. It is given that, assume, alright, assume that the inlet and exit area are equal. If the inlet and exit area is equal, Alright, area 1 equal to area 2. That means velocity 1 equal to velocity 2 because we have the same flow rate Q1 equal to Q2. So velocity 1 is equal to velocity 2. We can cancel. This is not 0 because this is the same term. Alright. And then leave it only head of pump, HP. So from here, we need to leave only head of pump. This is step number 3. Rearrange the equation. Leave it the head of pump to be the subject is equal to the whole term here go to the other side. Alright. So from here is P2 minus P1 over gamma plus Z2 minus Z1. Alright. So what is the P2? P2 is 600 kilopascal and P1 is 200 kilopascal. Just substitute the value 600 kilopascal minus 200 kilopascal over gamma of water which is 9810 plus Z2 minus Z1. So this is Z2. Alright. Minus Z1 which is 20. Alright, 20 centimeter convert to meter become right 1 2, so become 0.2 meter. 0.2 meter. The final answer should get the 41 meter. That means this pump, alright, I would like to illustrate that this pump can increase the water until maximum 41 meter. That is the power of the pump. Alright, until 41 meter. So from this one, step number 4 is that we need to correlate the head of pump with the power of pump. So by using the equation, work rate of the pump is equal to gamma QH of the pump plus efficiency of the pump. Remember, the efficiency of the pump always at the denominator side because it is input the efficiency. Right? So gamma of water here is 9810. The flow rate here, I think it is given to be 0.2 meter cubic. And head of pump we got earlier is 41 over, given the efficiency of the pump is 85. Alright, don't write here 85. You should make it divide with 100. 1 to 0.85. The final answer is, alright, 94.6 kilowatt electrical power required to pump for the pump to increase the water level up until 41 meter. Therefore, that is the final answer.